I will present my master thesis about level P complexity for Boolean functions. And first of all, let's start by dissecting the title. What is a Boolean function? So it's a function going from n bits that are 0 or 1 to 1 bit. And the input could look, for example, like this. So 0, 1, 0 when n is 3. And the Boolean functions can model yes/no voter systems and electrical circuits. So in the circuits, we have logic gates, and these are also the building blocks of all modern technology. And regarding voter systems, we have n votes that are yes or no, and then the Boolean function is determining the output of the election. So one example of a Boolean function is the dictated function, which is taking in n different bits, but actually just outputting one of them. So it ignores all the other bits. Another example is majority on 3 bits, which is 1 if there are more than 2 ones in the input, and 0 otherwise. So for this example, the majority is 0. So now that we know what a Boolean function is, we can introduce the concept of algorithms. So they query each index of the Boolean function a bit at a time. And they are adaptive, so the next bit query can depend on a previous bit value. And they seek to determine the output with as few bit queries as possible. And they will stop as soon as the output is known. So why are we interested in this, in determining the output with as few bits as possible? So one thing is that if we can determine the output of the function with just knowing the few of the bits and not all of them, we can save the time by just asking each. If we say that each question takes some time to ask, we save some time by not asking all of them. And also, if we think about circuits, it could be interesting to ask how much does a change in the input affect the outputs? How sensitive is the function? So if we have, for example, an error in the input, how much will it affect the outputs? And then this question of the algorithm is also relevant, because we could only need a few bits to determine the outputs. It has different sensitivity than others. And then lastly, if we consider the example of voting, it could be interesting to see how many of the votes we have to count before we know the result. So often when they count votes, in, for example, the US elections, they count votes for each state, and they have a prediction of who is going to win after they've counted an amount of votes. And so this we can do because we see after a while what the result seems to be, even if we haven't counted all of them. And this depends on how, for example, in which order we count them, and also how close the result is, of course. And then we introduce also the cost of an algorithm, which is how many queries are needed for this algorithm to determine the outputs given some certain inputs. So we go back to our example with majority on 3 bits, and this could be an example of an algorithm for this, which means that we first ask the bit x1, and then x2, and then if we need to, we also ask x3. So we want to find out the output with as little information as possible. And here we see 2 examples of some inputs where we don't know anything about the bits, and we don't know the output, but we want to determine. So we start by asking the questions. So in the first case, the first bit is 1, and then the second bit is 0, or also 1. And then we see that since both of them are 1, we can already determine the majority without having to ask the third bit. But for the other example, when we have 1, 0, 1, we have to ask all 3 questions when we ask them in this order. So the cost of asking of using the algorithm these separate inputs is 2 and 3 respectively. So again, a new concept is that if we have a Boolean function and the cost, how can we minimize the cost for the worst case inputs? So this introduces the concept of deterministic complexity, which we can see here. And it's defined as the minimum over algorithms of the maximum of the inputs of the cost. And for the example we just had with 3-bit majority, the deterministic complexity is 3. So this means that for the example we had with the algorithm, we saw that the highest cost was 3. And since the majority function is symmetric, which means that no matter the order of the inputs, the output will be the same. Actually, all of the algorithms for querying the majority function are the same. So in this case, the deterministic complexity will be 3. And then the next concept of complexity is level P complexity, which is how we can minimize the cost for the average case inputs. So in this case, we have a distribution over the bits where we pick each bit value at random with probability P. And the bits are independent and identically Bernoulli P distributed, which means that they take the value 1 with probability P and 0 with probability 1 minus P. And they are also independent of each other. So then the level P complexity is defined as the minimum over algorithms of the expected cost when X follows this pi P distribution. And note that we can vary the P. This means that the level P complexity is actually a function of P compared to the deterministic complexity, which was only a number. So now we will compute the level P complexity for this majority of 3 bits example. And first of all, we have to ask 2 of the bits, and then the 3rd bit is needed. So the cost of asking the first 2 bits is 2. And then we only ask the 3rd bit if the first 2 are different. So if we have 1, 0 or 0, 1. And this has probability P times 1 minus P plus 1 minus P times P. So the formula we get in the end is 2 plus 2P times 1 minus P. So we see also in this graph the formula, and it ranges between 2 and 2.5. We can see that in the endpoints, the minimum is 2. So this means that in this case, we will only ask 2 questions. And this is since if P is 0, we only have zeros in the input. So then we ask 2 questions. And then the maximum is 2.5 in the middle at P equals a half. And this means that on average, if zeros and ones are equally likely, we will ask 2.5 questions. So we might ask 3 questions or 2 questions depending, but on average it's 2.5. So now that we have introduced Boolean functions and algorithms and the complexities, we introduce our aim, which is to calculate the level P complexity for different Boolean functions. We have already seen the example of the majority function. And since the level P complexity is a function of P, we can also consider its properties, like is it continuous and differentiable in P? So actually, yes, it is continuous because it is piecewise polynomial. And I will explain more about this later. And what is the maximum of the level P complexity? So we saw that we computed the maximum in the case of majority on 3 bits. And this can be interesting for 2 reasons. It's both interesting to know what is the maximum complexity we have, what is the number of this, and to compare it to other notions of complexity. So for example, for majority on 3 bits, the maximum was 2.5, but the deterministic complexity was 3. So the maximum level P complexity is lower than the deterministic complexity. And it's also interesting to see at which point this maximum occurs. So for majority, it occurred at P equals a half. And but for other Boolean functions, it may be at P equals a half, P equals 1 or something else. So it really depends on the function. Then we want to see if there's a unique maximum for DP or if there are several. And lastly, maybe the most interesting question, does the optimal algorithm of the Boolean function depend on P? So this means that for small p, would we ask the bits in a different way than for large p? How would this change? So we move on to the next example, which is iterated majority. So here we use the building block of 3-bit majority 2 times. So we have 9 bits, and we take the majority of the first 3, and then the next, and the last 3. And then in the end, we take the majority of M1, M2, and M3. So here we see an example of how this function works. So in this case, we have 0, 1, 0, which is 0, 1, 0, 1, which is 1, and so on. And this gives in the end 0. But if we switch 2 of the bits, so if we switch the first and the 8th bit, which are shown here but marked in red, we have a different result. So in this case, the first block will have majority 1 instead of 0, but the other ones are the same. And this means that the majority of the whole function is switched from 0 to 1. And both of these examples have 4 ones and 5 zeros, but the result is different if we change the position of the bits. And this means that we don't have the same symmetry property as we have with majority, because there we could just switch the order and the result will be the same. But here we cannot blindly switch the order like this. We could still switch the order in the blocks and between the blocks, but like this we get a different result. And this is also interesting if you go back and consider again US elections, where we have that one potential presidential candidate can lose even though they have won the popular vote. So in this case, we have that the zeros lose even though they won the popular vote, because we have 5 zeros, but still the majority is 1. So even though this is a very simplified example, it's kind of the same structure going on. And then we go through some different algorithms for querying the bits for iterated majority. So first we take the simple algorithm, which is asking the bits in order, and they go to the next block if they already know the block majority. So first we start by asking 2 questions. And in this case, both of the bits are 1, so we know that the majority is 1. We go to the next block. And in this case, we have to ask all 3 questions. So M2 is 1. And this means since both M1 and M2 is 1, that the output is also 1, without having to ask the rest of the bits. But we try this algorithm also for another input. So in this case, we have to ask all the questions in the first block and all the questions in the second. And then since M1 and M2 have different signs, we also have to ask the last block. So we have to ask all the 9 bits. And is there a better algorithm than this? So there are, of course, many different algorithms. And for this particular input, we can see that we have a better algorithm just by asking the bits in another order. But we want to see if we have a better algorithm that could work better in general. So what happens if we start at this point after having asked 4 questions? Could we do anything differently from here? So we see that the majority in the first block, M1, is 0, and the first bit in the second block is 1. So they have different signs. And actually, when we know that the majority in the first block is 0, it would be better if the next block's majority also was 0, because then we would have to ask less questions. And since we have then 2 blocks here, one with unknown bit values and one where we know that one of the values are 1, then it's more likely that M2 is 1 than M3 is 1. So we should rather switch to block 3. And we try this approach, and then we get 7 questions instead of 9. And of course, we can also find examples where this algorithm is worse than the other, but I believe, or I know that this algorithm expected cost will be better, and I will show this. So I explained first a bit more about the algorithms. So as we said before, A1 is a simple algorithm. It just goes on and it never switches. And then we have three different ways on how to switch. So we have A2, A3, and A4. And then if both the majority in the first block and the first value of the bit in the second block are the same, there's no use in switching. But if they are different, we could switch in some different ways. So for example, if n1 is 0 and x21 is 1, we switch for algorithm A2. But if m1 is 1 and x21 is 0, we stay. And A3 is the same but different, and then A4 switches in both cases. And then we show the expected cost of these four algorithms, which can be seen here in the graph. And we see that they range between 4 and 6. And we also see that it's very hard to differentiate between these four costs. So for that reason, we show a new graph where we have the differences between them. So we subtract the expected cost of the algorithms with the expected cost of A4. And here we see that the top graph, which is the expected cost of A1, is it's the highest, so it's the worst in the interval. And then A2 and A3 are the same bottom, they are mirrored in p equals half. And then that A4 is the lowest in the whole interval. So still there is not so much of a difference, but A4 is in fact the lowest. So this means that A4 is the optimal algorithm. Recall that A4 was the one where we switched in both cases. And this means that the expected cost of A4 will be the result of the level P complexity. So here we see the result, which is this 8-degree polynomial. And we also see the plot in the graph. And we see that the minima are 4 at p equals 0 and p equals 1. And this means that when p equals 0, we have, for example, all zeros. And in this case, we only have to ask 4 questions because we ask 2 of the blocks and 2 of the questions each in these blocks. But when p equals half, then we have the maximum of 6.1875. And in this case, when zeros and ones are equally likely, we will ask a little over 6 questions on average. So now that we have shown some examples of how the level P complexity can be computed, we discuss the more general question of how can it look generally. So we know that it's going to be continuous, but both of these graphs are continuous. So are both of them valid or just one of them? So as I mentioned before, the level P complexity is piecewise polynomial. And this is since it's a minimum over all algorithms of expected costs. And the expected costs are actually polynomials. And this is since we have a finite Boolean function and we have a finite number of inputs, and each of them have probabilities, which will be a sum of the product of p and 1 minus p terms. So in the end, this will be a polynomial. And when we have the minimum of these, the level P complexity might not be just a polynomial in the whole interval. It might intersect in some points, but it will be piecewise polynomial. And this means that probably the right graph is more likely to be the level P complexity because the first one is nowhere differentiable. So then we have a lot of intersections of different polynomials. But the second one seems to be the combination of 3 different polynomials. So now we know that it could probably look more different than what we had so far. So far, for example, we had a concave function with a maxima in the middle. And we want to see if we can find a function that has an algorithm that depends on P or that has 2 maxima. So we want something like this. So we try to construct a function that will give this result. So here we have 5 bits, and 3 of them are in block A and 2 of them are in block C. And In block A, we have subfunction fa, which is 1 if the 3 bits are different, and 0 if they are the same. And in block C, we have 2 bits that are, and the subfunction is 1 if the bits are the same, and 0 otherwise. So these are kind of opposite functions, which is actually the key to get the behavior that we want later. And then FAC, it is the combination of these 2 subfunctions. So it's 1 if any of them are 1, and 0 only if both of them are 0. We show some examples of how the function works. So here we have all zeros, FA is 0, FC is 1, and then FAC will be 1. Here we switch the 4th bits to 1. And in this case, both FA and FC are 0, so FAC is also 0. And then here we switch the first bit to 1. And in this case, both FA and FC are 1, so FAC is also 1. And lastly, when we switch both the first bit and the 4th bit to 1, we have FA is 1 and FC is 0, so FAC is 1. So we show some algorithms now of how to evaluate this function. And the first one is if we first ask all of the bits in A, and then the bits in C if needed. And we call this TAC. So we show this here for the 4 examples. First, we have to ask all of the questions in the first example. Then for the second one, we also have to ask all of them. Then for the third example, we see already after asking the 2 first bits, we know that FA is 1. So we already know that FAC is 1 without having to ask the last block. And the same goes for the last example. So these 2 look the same now, but actually the question marks hide different values, but since we don't see them, they look the same. So we get 5, 5, 2, and 2 questions asked. Then we try the other algorithm, which is to first ask the bits in C, and then A if needed, which we call TCA. And in this case, we have that FC is 1, FAC is 1 with 2 questions asked. Second one, we have to ask all of them. The third one is the same as the first. And then the last one, it's enough if we ask 4 questions to know the result. So we get 2, 5, 2, and 4 questions asked. So, but now these were only 2 of the possible algorithms. We generate all of the 52 possible ones, and then we take the expected cost of them, and we get 39 different polynomials, which we have plotted here in the graph. And there are quite many of them, and there are a lot of intersections. It's a bit hard to differentiate, but thankfully, we only have to look at the bottom 2 because we are minimizing. So it's enough that we see that there's the convex purple graph and there's a concave red graph that are the minimal ones. So we show them separately here in the graph. And actually, these 2 polynomials correspond to the 2 algorithms that we discussed before. So even though we now generated a lot of different algorithms, only these 2 were relevant in the end. And this is quite interesting because we see that when P is in the middle, P0 is the best. And this is when it's best to first ask the bits in A and then C if needed. So this is because when P is around a half, it will be more likely that the bits are different. So then it's more likely that FA is 1 than FC. So we should start by asking A. And then if we fuck up, we have to ask also C. And then when P is small or P is large, then it's better to ask C first and then A. So this is because when P is, for example, 0, then all bits are 0. So it would be better to first ask the block where they should be the same. So now we show the level P complexity, which is a combination of these 2 different polynomials. And we see the graph here as well. And we note that the algorithm does depend on P in this case, and also that it has two maxima. And the maxima are in fact at the crossover points. And we see that the minima are 2 at p equals 0 and p equals 1. And this is, as I said before, because then we ask the 2 bits in C, and we know the results. And the maxima are a bit over 3. So then we would ask more than 3 questions when we have the crossover between the 2 algorithms. So to summarize, we have now calculated the level P complexity for functions majority and iterated majority. And they are continuous, differentiable, and they have a unique maximum. Actually, they are both symmetric and also have the maximum at p equals a half. And then we constructed a new function so that the level P complexity has 2 maxima. So in this case, the optimal algorithm depends on P, and in the intersection points, the level P complexity is not differentiable. So future work could be to calculate level P complexity for more different Boolean functions. So for example, in my thesis, I have done it for some other examples that I couldn't bring up here, but essentially most of them have very similar results. So it would be interesting to see if we can find other Boolean functions that have different results. So for example, there's this wiki page called the Boolean Zoo, where there's a huge list of a lot of different Boolean functions that one can just try. There's also this very complicated Boolean function, percolation, which Jeff is expert on, and that we could look at more. And then you can also do like we did here, construct new functions with some interesting properties. So go after exactly like, we want something that looks like this. How can we construct this? And that would also be very interesting to see. Yes, so thank you for the presentation.